Imagine reading a story. You don't just process each word in isolation. You remember the characters, the setting, and the plot points that came before. Your brain holds onto context to build meaning. For a long time, computers struggled with this. Standard neural networks saw the world as a series of disconnected snapshots, treating every piece of data as if it were the first. But then came an idea. With roots in early neuroscience observations of feedback loops in the brain, the Recurrent Neural Network, or RNN. Instead of a simple one-way street from input to output, an RNN has a loop. This loop allows the network to feed a summary of what it just saw back into its own process. It creates a form of memory, a hidden state that carries information forward through a sequence, step by step. This architecture, formalized by pioneers like Jeffrey Ellman, was a natural fit for the rhythm of our world, for language, music, financial markets, and anything that unfolds over time. But this new memory was fragile. A deep, fundamental problem quickly became apparent during training, a process called backpropagation through time. To learn, the network had to look back at its mistakes and send correction signals backward through the sequence. But with each step back, that signal was multiplied.
Over long sequences, these repeated multiplications cause the signal to either shrink to almost nothing or explode into chaos. The first case, the vanishing gradient problem, meant the network effectively developed amnesia. It couldn't connect an event from the start of a sentence to a word at the end. Its long-term memory was gone. The second case, the exploding gradient problem, would crash the training process entirely. For a while, it seemed these issues would forever limit RNNs to remembering only the most recent past, a critical roadblock for true understanding. The breakthrough arrived in 1997 from two researchers, Sepp Hochreiter and Jürgen Stimhober. They designed a far more sophisticated type of RNN called a long short-term memory network, or LSTM. Think of an LSTM unit as a tiny, intelligent data gatekeeper. It has three specialized gates that manage a dedicated memory cell. First, a forget gate looks at the existing memory and decides what old information is no longer relevant and can be discarded. Then, an input gate determines which parts of the new incoming information are important enough to store. Finally, an output gate decides what specific piece of the memory is relevant to the task at hand. This elegant system gave the network precise control over its memory, allowing it to protect and carry critical information over very long distances. A few years later, a simpler, more efficient version called a GRU, or Gated Recurrent Unit, was developed, making these powerful models a cornerstone of AI for years. This architecture powered a revolution in machine translation, voice assistance, and sentiment analysis. But the story took another turn in 2017 with the arrival of the transformer. This new model used a different mechanism called self-attention, allowing it to process entire sequences in parallel and capture complex relationships more effectively. Transformers quickly became the dominant force in AI. So, is the RNN obsolete? Not at all. Its legacy is profound. Its step-by-step nature makes it incredibly efficient for tasks that are inherently sequential, like generating text one word at a time, or making continuous predictions from a stream of sensor data. Where a large transformer might be overkill or too slow, a lean RNN can excel. Today, we see powerful hybrid models, combining the local focus of RNNs with the global view of transformers, and they remain vital in fields like algorithmic trading and predicting patient outcomes in healthcare. The RNN wasn't the final destination, but a crucial chapter. It taught us how to build machines with memory, a lesson that continues to shape the ever-evolving story of intelligence itself.